one of the times this semester where you all feel relieved that you're going to see me on a video doing fieldwork instead of being out here with me. It is snowing just outside Sherbrooke today, just off the Highway 10. I've come all the way out here to get into the Appalachian Fold and Thrust Belt. We're just at the edge, and if you've ever driven out this way, you know you go, the 10 takes you across the flatlands of the St. Lawrence lowlands, and then you start to see a little bit of topography, a little bit of hills come up when you get out to what we call the eastern townships. And we come through Mount Orford, and then out a little bit beyond that, everything is hilly. And you start to see big outcrops through Mount Orford and out to the east of this beautiful slate, which is Magog Formation. It's black slate. And today we're going to look at some of the deformation that occurred during the Appalachian orogenies and learn how to measure folds in the Magog slates. Okay, right here on this outcrop of slate, you can really see the two features that we're going to talk about today. So the first thing you'll notice about these outcrops is this nearly vertical plane, which is the cleavage plane of the rock. That's where the rock is splitting off into sheets. And that tells us that on the microscopic level, the clay minerals in this rock, or the micas, or whatever the sheet silicates are very well aligned in this plane. And that's they like to split even on the molecular level that way. And then the splits between them also are parallel, so it gives the rock this very strong cleavage. And that's what we associate with slate. That's basically the characteristic of slate. The other thing you can see where I'm standing is that there is a color banding in the rock from dark gray to lighter gray. And sometimes it's a little bit gradational. Sharp on one edge and gradational, sharp, gradational, sharp. This is actually the original bedding of these, what would have been shales that were deposited in the deep sea in front of the Appalachian origin. And the lighter gray is a higher proportion of silty material, maybe feldspars and quartz. And the darker gray is just clays and maybe some organic material that gives it that deeper, blacker color. So in this case, in this part of the outcrop, that slaty cleavage is roughly parallel to the compositional banding that is the original bedding layers. So when the clays are actually deposited on the seafloor, the little tiny grains, only 2 microns in size, 0.002 of a millimeter, they settle down, and they're so small and so light in the water that they just arrange themselves a bit randomly on the bottom and make a loose layer of poorly oriented clay. And I also added some sand grains in here because it's not pure. As the layers build up, they start to compress a little bit and apply some weight. The pore water that's in between the little grains of the sediment starts to squeeze out. With increasing burial, the gravitational load from the weight of the sediments above really starts to flatten. And if the sediments are buried deeply enough that they're starting to warm up, then those little tiny 2-micron clay grains will start to grow into slightly larger micas. And as they grow, because of their leaf shape, they're just little flakes, they will expand like little sheets of paper in the direction perpendicular to the strongest stress. So in this case, if the strongest stress is that vertical loading from the additional layers of sediment above, then they'll grow horizontally, which would be parallel to the original depositional surface. So here we have a beautiful cleavage in the rock, which is the alignment of these little mineral grains, and it's parallel to the compositional layering, which is the original bedding in the rock. Now, what about the case where we're in a tectonic collision zone? So that instead of the vertical stress being the strongest, we actually have a horizontal stress from those continents colliding, which is stronger than the vertical stress because of the burial depth. So those little micas will grow, again, sensitive to the maximum principal stress in the field. So in this case, because we have a horizontal stress, the micas grow into vertical planes. And that means I've also put here that these sediments are going to be buckled and folded by the compression, by the tectonic compression. So that means that these cleavages will line up so that they're actually perpendicular to bedding in the hinge area of these folds. And as we go down the limbs where the bedding is more steep, the cleavage is near parallel to the limbs in those parts. And then as the bedding turns, the cleavage carries on with its vertical orientation and is perpendicular in the hinge of the fold.
And because this is the definition of the axial plane of the fold, is the plane containing hinge lines from each of these layers. The cleavages, which we can physically measure in the field, end up being a useful geometric proxy for the orientation of the axial plane of the folds.
What can we learn about the depositional setting of the Magog Group? So these are thought to be deep water rocks. They're very fine-grained. They're substantially, the biggest component of the grains is phyllosilicates, which would have been clay minerals in the original rock. They've now been metamorphosed to low grade, approximately low green schist facies. So a lot of those clay minerals will have been recrystallized to a more stable mica. So there are a lot of very fine sedimentary structures in this rock that also tell us about the depositional setting. We have really fine crossbeds and multi-directional crossbeds that are evidence for currents on the bottom of the ocean. A lot of paleontological work has been focused on the Magog Group with a type of fossil called graptolites. Now, graptolites are, for a long time, it wasn't really known what kind of animal they were, but they are little sawtooth shapes,
flattened tubes that hosted a worm-like organism that lived on the seafloor and filter-fed.
But they're really abundant in these deep water shales, so they must have been very abundant in the Magog, in the sea during the deposition of this rock. We also see a lot of these very coarse crystals and clusters of pyrite, and so pyrite is an iron sulfide, and this particular pyrite has a little bit of a silvery color and a slightly different shape than the normal pyrite cubes. It has a lot of different shaped crystals that are characteristic. The color and the abundance of those other crystal shapes suggest that it might even be an arsenopyrite. That's a iron sulfide with quite a bit of arsenic substituted into it. So the sulfur and the arsenic are characteristic of having organic material in a reduced environment, again consistent with deep water where there's very low oxygen content in the water, and so that was buried along with the clay sediments to make these black shales. And in fact, the black shale color is characteristic of deep water, organic, rich, reduced environment shales. And because of that reduced environment and low oxidation, a lot of metals can be deposited in these things. And so because of that, black shales are used the world over as these environmental indicators, and also to tell us a lot about the composition of the oceans in the past. So a lot of those metals that are rich in these shales, they carry the record of things like continental weathering that tell us, what the climate was like on Earth during those times, and tie together to the larger element cycling that goes on in the environment. So black shales are very useful for a record of life and also a record of environmental conditions deep into the past. Well, I'm not in a national park. I'm in the parking lot of a bar. So I'm definitely going to take this home. It just fell off into my hand, but what a gorgeous big crystal. All right. This is a very tricky part of the outcrop, and it's actually the key to everything here. So I hope you can see that there's still this very strong vertical cleavage, but you can see the splits in the rock running this way. But we also have the subtle banding here. These repeated stripes of different compositions. And in fact, some of these bands have a whole bunch of these big fat pyrite crystals in them. And those are representing beds that had originally like a lot of sulfur in them. So that's another clue that this is a compositional layering. I can even see a little bit of gradation here on some of them. That's the original bedding. So in contrast to the first place we saw it, here we have a steep slaty cleavage, which is still subvertical, but the bedding is now dipping much more gently. And in fact, as we go across the outcrop this way, it gets even more gently dipping. Because I think this is a really essential part. I'm going to take some measurements here. This is a beautiful exposed split face on the cleavage. So now the bedding is a little bit harder to measure. I need to find an exposed surface. And since this is a compositional band that can follow along this sharp edge here, I think this is actually the surface here. So I'm just going to get underneath it. behind these leaves you can see where the bedding, which was dipping off to the west where I just measured it, turns over to make the hinge of an anticline and starts dipping the other way. Look at that. What happens right in the hinge zone, we see nearly perpendicular relationship between those steep cleavage planes and the bedding, which goes through a shallow dip as it bends around the fold hinge area. So I'm going to take some concentrated measurements right here. So these bedding planes, they're obviously really planar, but they appear to make an arc because of the curvature of the outcrop here. So again, I need to find a place where the bedding plane itself is exposed to put my compass on it. And I think this is the best surface here. And although it's the shallowest dip, I can actually see that it is dipping a pretty steep angle. I would guess is 35 or 40 degrees into the direction of the outcrop, so away from me here. So that is the minimum dip that this bedding goes through. That means that the fold itself is not horizontal, or else it would go through a zero dip. But that fold has been tipped toward what's that going to be, northish, like that, so that the minimum dip that the bedding ever has is right in the hinge. And let's find out what it is exactly. That's the shallowest it ever gets. I'm going to measure the cleavage plane here too, just to make sure that that's not varying.
Well, that concludes our very quick orientation to the Magog slates and a little introduction to axial planar cleavage, how it forms during folding, and its relationship in terms of the angle of intersection to bedding as bedding curves through a series of folds.
Bonjour tout le monde, bonjour de beau Sherbrooke, où il fait super beau aujourd'hui. Je suis ici pour faire des travaux en terrain pour vous.